next have Pierre Desjardins, who's with C12 Quantum Electronics. They're developing processors capable of handling large-scale quantum, I love that word, quantum calculations. Pierre? Oh, he bought quantum calculators with them. There you go.
Thank you. Hello, everyone. We are C12, and we build reliable quantum computers. Quantum machine will solve highly complex computing problems, the problems that are out of reach of even the most powerful current or future supercomputer that will change our lives. The fundamental problem of quantum computer is that quantum material interact very easily with their environment. Ideally, a quantum bit needs to be in vacuum. No defects leads to no perturbation. No perturbation of the qubit means no error. A brilliant research group, how can we achieve this, A brilliant research group at École Normale Supérieure had a simple idea: to find the perfect material for a qubit. After 10 years of research, they discovered that carbon nanotube extraordinary properties can make qubits isolated yet addressable. At C12, we are building it in a very scalable way. Our qubit is very small, and it's a semiconductor technology. What would be the first application? First, we will use our quantum computer to simulate quantum chemistry reaction with greater accuracy. We have a first hydrogen-related project with Air Liquide. Second, using Atos programming, we will accelerate the convergence in optimization problem. In parallel, in 2022, we will demonstrate trustable results on a 5-qubit demonstrator and make it available to anyone in the cloud. Our first product will be a quantum accelerator in 2025, an accelerator of a classical system. Then, by scaling the number of qubits, we will be able to offer a large-scale, error-corrected quantum computer by the end of the decade. Mathieu and I founded C12 in 2020. It's a unique combination of scientific skill and business excellence. And well, as it is my twin brother, a good deal of trust. Octave Clabin, founder and chairman of OVH Cloud, supported us from the start, thrilled by our unique and very promising approach. With our senior team of scientists and quantum engineers, 19 people in total, we reimagine our quantum computer are built. Silicon enables the emergence of classical compute. It's time of carbon to do the same for quantum. Thank you very much.
Thank you, Pierre, for coming here. Judges?
You just mentioned quantum chemistry and drug design as possible applications. What's your timeline of getting proof of concept on that? I pose that question because unofficially Google just delayed customer contacts for these applications to 2029.
So we are really focusing on building a high-fidelity quantum processor. So our processor will be a prime candidate for this intermediate era where you have intermediate scale quantum processor and still noisy. But they can offer an advantage to speed up some calculation. So that's why, for example, we are already working with Air Liquide. Finding the right application will be related to hydrogen. And so with Air Liquide, it's a 2-year project. For the optimization, it's a 3-year project. Then at the end of the project, I think we will have a very good understanding on what should be the chips that we have to make. And so it will be 1 or 2 years later.
I'm curious to understand your approach versus others, fault-tolerant architectures in photonics, spin qubits, etc. Can you place it a bit in context?
So at the end, what is key is high fidelity. if you want to do some quantum error correction, but you start with low fidelity, you will need a lot of overheads to actually achieve your logical qubit. And the second thing is that we have a very special feature in our architecture, which is all-to-all connectivity, meaning that any qubit can be connecting to any other qubit at any time, and this is solid-state technology that enable this. And if you combine all-to-all connectivity and high fidelity, you can use some error-correcting code that require very limited overheads, so between 10 and 20 qubits, physical qubits to make a logical qubit.
It's not the only metric, but it's an important one. How many qubits will you have on 25 and 2030? Because, for example, for people in the audience, 2 weeks ago, IBM said they had 127. And of course, they're going to double every year. That's what we promised. So how will you catch up with that?
So what we think is that what is the most important metrics is the quality of the qubit. It doesn't help to have more qubits if your qubits are of bad quality. So we're not that afraid about the number of qubits that IBM is actually committing on. And to give you an answer, so we are targeting NISQ devices by 2025, so between 50 and 100 qubits. But because they will have this high fidelity and high connectivity, this will be an unparalleled performance.
Thanks very much, Pierre. Before you leave, any final ask of the audience? What are you looking for?
So we just raised our seed round in June, and right now we are looking for, so we have already two, let's say, applications, one in quantum chemistry, the other one in optimization, and we are still looking for forward-thinking companies that want to understand how quantum computing can accelerate their business.
Well, I see a lot of yellow and red badges in the audience, so I think this should be as good a place as any to find folks like that. Good luck. Pierre Desjardins, ladies and gentlemen, not afraid of competing with IBM. I love it. Here we go.